Okay, so hello everyone. Welcome to our UNAB Journal Club. This week we have Rodrigo Olea. He's going to talk about conformal renormalization in AdS gravity. So Rodrigo, you have around 45 minutes, and if anybody has questions, just I think can interrupt Rodrigo. Okay.
Thank you very much, Felipe, for such nice introduction. And I will try to. It's the second time I'm talking about this topic, and so I'm trying to systematically introduce a new concept that I will loosely call conformal renormalization. I will try to explain what is the issue about. So I was thinking of making a short review on standard holographic techniques and the relevance of holographic renormalization in order to produce a sensible physical information from gravity theory with AdS asymptotic behavior. But because most of the audience had at least once heard about it, I will pass through, I think, faster than expected. And okay, so I will briefly review the standard holographic construction and holographic techniques in AdS gravity. I will introduce the need, and I will make some consideration that make you believe that there should be some alternative renormalization scheme to AdS gravity. I will call it counterterms with a K, that is not a typo. And I will stress the fact that whatever we do, we see the Weil tensor appearing at the boundary at the level of the charges in a very straightforward way. And also, I will introduce some sort of conformal-like structures in the bulk. I mean, the relevance, the appearance of the Weil tensor in the form of the renormalized AdS action, AdS gravity action. I also briefly comment on the connection to the concept of renormalized volume in the mathematical literature. And of course, the punchline will be the appearance of this new concept of conformal renormalization. So what is this about is a standard AdS-CFT correspondence is the fact that in order to compute correlators in the boundary CFT, you have to evaluate the classical action, classical AdS gravity action, as you approach with your fields to the value of the field at the boundary. So this is a Gubser, Klebanov, Polyakov, Witten usual formula, and whenever you do it for the phi naught, that is the metric, whenever your field is the metric tensor itself, you have to carry out some renormalization procedure because this is the appearance of divergences at the level of the on-shell action is due to the fact that the asymptotically AdS spacetime had divergences as you approach to the boundary. So the standard way of dealing with these divergent terms is the fact that you express the metric as a power series, and in order to make this divergent behavior manifest, you write it down in Poincaré-like coordinates. The boundary here is located, the boundary of the spacetime is located at z equal to 0. So of course, there is a divergence of order 2 as you approach to the conformal boundary. Because, of course, the metric at the boundary can be defined up to a conformal factor. And this G metric, Gij metric, as X are a regular expansion in powers. Usually in Einstein gravity, you will consider only even powers of the Z coordinates. In terms of course, these coefficients that you see here, they are supposed to be solved in terms of the holographic data that is you fix at the boundary. Keep in mind that the corresponding CFT living at the boundary is a field theory living on a curved space-time, but it can be that is anyway fixed. The matrix is fixed at the boundary. So the G naught is actually a fixed metric living where the CFT lives on. And given this holographic information, you are able to reconstruct the space-time order by order, solving the Einstein equations. So the idea is that you are able to determine, to a certain extent, you are able to determine all these coefficients in terms of the holographic data. Usually, as an example, I will show how you determine the first coefficients out of the holographic G0 metric. So because of the asymptotic behavior of ADS spacetimes, asymptotically ADS spacetime, you have to carry out a procedure which is called holographic renormalization, which is a very well-defined procedure. It's a very systematic way of dealing with divergent terms at the level of the action and the variation of it. So you have the standard Einstein-Hilbert action with negative cosmological constant. You have, as usual, to define a well-posed action principle. You have to consider the addition of the Gibbons-Hawking term. The addition of the Gibbons-Hawking term is essentially the trace of the extrinsic curvature of the boundary. You have to keep in mind the fact that you are foliating the spacetime as a series of concentric cylinders in the Z coordinate, in the spatial coordinate, a spatial normal to the boundary. And you also have to consider, because of the behavior of the on-shell action, you will need the addition of local counterterms, which are given by this. It's a series that will show what are the first terms in the series, how to find them. And they are usually expressed in terms of the boundary metric, the boundary curvature, and essentially, eventually, covariant derivatives defined in the boundary metric. So in doing so, you're able to define such a thing as a quasi-local stress tensor. Whenever you have the Gibbons-Hawking term, you define the canonical momentum associated to the normal foliation of the spacetime. And if you add counterterms, you obtain a renormalized version of the quasi-local stress tensor, and which considers the first is the addition of is the canonical momentum, which is linear in the extrinsic curvature. I will emphasize these aspects in one slide later. And from the standard definition of quasi-local stress tensor, you are able to obtain holographic quantities just by simply rescaling the Brown-York stress tensor at the boundary. By proper rescaling of this quasi-local stress tensor, you're obtaining quantities, correlators, which are defined in terms of the G0 metric. And these contain information on the holographic information of the theory. In particular, something that is useful to identify the corresponding CFT living at the boundary, it can be done through the analysis of the corresponding Weil anomaly. These are the first example people found even in early times of ADS-CFT correspondence. So what are the usual counterterms that you add on top of the Gibbons-Hawking term? There is a series which is increasing in numbers of derivatives. So in principle, you have a term that does not contain derivative. It's like cosmological constant at the boundary. And you have sort of Einstein-Hilbert term at the boundary as well. So it's a two derivative term. Eventually, you have curvature square terms as well. That means four derivative terms and so on, so on. And essentially, the motivation for us have been trying to give a alternative answer to the fact that in this formula, you can see three dots at the end, this ellipsis, and the fact that no one knows how this series should go on as you increase the dimension, or whether there is a closed form for this counterterm series. The other thing is the fact that I'm emphasizing the fact that the standard Brown-York stress tensor have this structure that is first contains the canonical momentum associated to the radial foliation of the spacetime. So it's linear in extrinsic curvature. So it's a precise combination of linear terms in the extrinsic curvature plus the addition of local intrinsic counterterms that which produces, in turn produces local contributions, intrinsic contributions at the level of the stress tensor. So the first thing I wanted to emphasize is the fact that this stress tensor is linear in the extrinsic curvature in the usual procedure. And that also the fact that there is no general form of the counterterm series for arbitrary dimension. As you can expect, as you can imagine, this is already difficult for Einstein gravity, let alone for higher curvature, higher derivative gravity theory. So in order to try to motivate an alternative procedure, I will briefly remind you of some observations that people have made in the literature. The first observation is based on a paper around 2004, where people were reformulating this holographic renormalization procedure. In this paper by Papadimitriou and Skenderis, it was strongly emphasized the fact that a Dirichlet boundary condition, keeping H fixed at the boundary, does not really make sense in asymptotically ADS spacetime. Why? Because if you analyze the asymptotic behavior of this metric, you will see, I mean, as it was emphasized in the Pfefferman-Grafenham form that I was showing before, there is a divergence of order 2. So it does not really make sense to try to fix this metric at the boundary because it's divergent. The only thing that you can truly fix at the boundary is the conformal data, is the G0 metric, because as I was saying, it's the one that is kept fixed at the boundary because it's where the CFT is living on. So these people were able in this paper plus other papers that follow, they were able to link the renormalization procedure to a well-posed variation, to the existence of a well-posed variation principle in terms of G0 metric. So if you try to define a well-action principle, a well-defined action principle for the G0 metric, you will realize that you are inducing divergences that you need to cure. And in order to cure the variation principle, you have to add counterterms. So in this way, you don't think any longer as the renormalization procedure and the well-posed action principle as two separate problems. They are all together. So necessarily, everything should come in as a single package. So, and there is a very blissful accident in ADS gravity, which is the fact that the extrinsic curvature had essentially the same asymptotic behavior as the boundary metric, the full boundary metric, this H that I'm showing in this transparency. And essentially, the extrinsic curvature had also the same behavior as this H metric at the boundary. And you understand this in the limit, for instance, in the limit of, in the flat limit of the theory, where you take L going to infinity. You understand that this accident will not be longer true in the asymptotically flat limit. This was also emphasized in a recent paper by Witten, essentially claiming the fact that there is this totally umbilic condition for the extrinsic curvature that relates the linear order between the extrinsic curvature and the metric at the boundary. So this can open the possibility of you to start thinking of a series of counterterms, but of a different sort. Why of a different sort? Because instead of thinking of purely intrinsic terms that you can add to the action, you can start considering that you could add boundary terms that depends on the extrinsic curvature, as long as you cure the divergent terms that appears at the level of the action. And there are two ingredients, essentially, as long as the variation of the action is holographic. What is called holographic? That's the reason why I put in these italics, because you can think of other way of renormalizing the action, and anyway, the variation of the action will be finite and will be expressible in terms of variation of the G0 metric, because this is the properly defined holographic principle. I mean, in the standard holographic renormalization procedure, the aim of the whole method was being able to express the variation of renormalized action in terms of the G0 metric, and this variation of the action to be finite. So we are satisfying both the requirements. So this is what I'm simply saying. The variation of the action is finite and is expressible in terms of variations of the source at the boundary. The other piece of evidence comes essentially from a definition of energy in AdS gravity, which is conformal mass. Whenever you think of conformal mass, is actually something that was proposed by Ashtekar-Magnon in 4 dimensions in the 80s. And it was extended by Ashtekar and Das in 2000 to higher dimensions. What is this, the conformal mass definition? It's essentially that you're able to compute the mass of a black hole, which is asymptotically AdS, by projecting the electric part of the Weyl tensor. What is the electrical part of the Weyl tensor? The Weyl tensor had four indices, and it had the skew-symmetric properties of the Riemann tensor. And if you contract the Weyl tensor with two normals to the boundary, this n is normal to the boundary, so it's radial. It's got a single component. So it will leave as a consequence two free indices, which have to be orthogonal to the normal. So they are leaving these ij components are leaving essentially are components of the boundary. If you use this definition for the energy of an asymptotically AdS black hole, you're able to compute Schwarzschild AdS mass and Kerr mass and angular momentum. Everything works fine. But you have to consider the fact that the electric part of the Weyl tensor, because of the properties inherits the properties of the Weyl tensor, is traceless. So necessarily, this had to differ by a holographic quantity from the standard stress tensor that we were computing before, because we know that the stress tensor contains the information about the Weil anomaly, for instance. In the simplest case, in 5 dimensions, people were studying these sort of things, and they realized that the electric part of the Weil tensor differs by a holographic term that contains the information on the anomaly. But let's think for a while that this is the simplest case. Let's think for a while that these two things are practically the same up to a term that corresponds to holographic information. So if you think that they are essentially the same terms, that means that if you write down the Weil tensor in terms of the curvature of the spacetime, you will realize that the electric part of the Weil tensor is essentially linear in the spacetime curvature, in spacetime Riemann tensor. So if you use Gauss-Corazzi decomposition to relate some intrinsic quantities with extrinsic quantities and these components of the Riemann tensor of the spacetime, you will realize that the stress tensor is actually quadratic in the extrinsic curvature. Funny thing, because I just told you some slides before that in the standard holographic renormalization procedure, the Brown-York stress tensor is just linear in the extrinsic curvature. This sounds like contradiction, because here we realized at the conclusion that the stress tensor had to differ by a holographic quantity from the electric part of the Weil tensor, and we realized that we could express it in terms of quadratic terms of the extrinsic curvature. And this is not surprising, because at the end of the day, we will realize that one of the expressions is a truncation of the other. It's a consistent truncation of the other up to the holographic order. You can think of all these quantities as an infinite expansion, but in this infinite expansion, only some of the terms will be relevant, because you have to use a power counting argument, and you have to power count the series until the relevant order, and the relevant order is just a holographic order. So all these quantities, at the end of the day, they are the same up to the holographic order. So this is just an argument to tease you with the fact that you could start thinking on the fact that standard counterterms are just the truncation of an expression for the boundary terms which could be nonlinear in the extrinsic curvature. So this very sort of basic argument opens the possibility for you to consider boundary terms which are nonlinear in the extrinsic curvature, which could have been heretic in thinking in the way I was presenting the things before. Are the questions this far? Okay. So what are these boundary terms which contains the extrinsic curvature in a nonlinear way? They are actually in the even dimensional case, even bulk dimensional case, is very simple to consider the existence of something that's called the Chern form, which appear. I will briefly review this connection to topological terms we were dealing before. Essentially, it's a polynomial of the extrinsic and intrinsic curvature whose coefficients are given in terms of a parametric integral. These are the typical tricks to define Chern-Simons forms. And So as you can see, is essentially a non-linear expression of the extrinsic curvature. Funny thing, because you can consistently truncate up to the relevant order, that what we will do it before to show the equivalence with the standard holographic randomization procedure. Of course, this is far more difficult to do it in the odd-dimensional case, odd bulk-dimensional case. This is an object that didn't exist in the literature before. It's not related to topological terms. I would say it's closer related to the existence of extensions of Chern-Simons forms, because this is if you're considering an odd-dimensional bulk, you have to consider a boundary which is actually whatever you add as a boundary term have to be even form, even dimensional form. So this is a funny double parametric integral, but then you understand some connection with Chern-Simons standard Chern-Simons densities. So it's not exactly, we have not been able to exactly trace it to some mathematical object in the literature, but it's a good proposal, and we have shown that it works in many situations. So essentially, the only thing that you have to do is fixing the corresponding couplings of these terms. And in a series of papers, we showed that we were dealing with the renormalization problem of Einstein-AdS and Lovelock gravity, and essentially it was always the same form of the boundary terms. The information about the theory was contained in the corresponding coupling, sort of universality of the renormalization procedure. What is this connected to? Is connected in the simplest case to understand is the even dimensional case in the bulk, which these terms are connected, of course, to the existence of topological terms. Some work we were doing with Rodrigo Olea and company in the far past, but it was convenient to express it in this way because it was the only way you could prove somehow the connection to holographic renormalization procedure. So this is based on the standard techniques homotopic. This is an explicit representation of the homotopy operator, because you have to deal with the fact the exterior derivative of a Chern-Simons density associated to a connection of a group is essentially the trace of, is a topological term, is a trace of the field strength to a certain power. And whenever you try to find an explicit realization of a Chern-Simons form, you end up with this parametric integral, like interpolating between the trivial connection, that is 0, and the corresponding dynamic field. So because of global issues, these two terms differ at most by topological numbers. Because if you integrate a topological term, it will produce a topological number, like the Euler characteristic for the Lorentz case, plus the corresponding Chern form. So this, of course, this existed in the literature. We didn't invent anything at all, but we just used it in a different context. Because we have evidence that we were able to renormalize using topological terms, we just translate it into terms which is dependent on the extrinsic curvature. And this was a previous step required in order to compare with to the standard holographic renormalization procedure. In the odd dimensional case, it's far more complicated and it's more intricated, and you can express an extension of a Chern-Simons form that depends actually on two connection fields. And you can interpolate between them in this trivial way, in a linear way, in such a way that for t equal to 0 is A bar, and T equal to 1 is A. And this has had an interesting splits in two parts, plus a contact term, which should live at the boundary. This is what is called transgression form. It's a gauge invariant object. It's a gauge invariant extension of Chern-Simons form. And the interesting thing is that if you consider such a thing, you can always write it down in terms of a Chern-Simons form associated to one connection field minus the Chern-Simons form associated to the other connection field plus contact term where these two things talk to each other at the boundary. And I'm just showing this to make manifest the fact that here is you use this trick of the double parametric integral in the representation of this contact term, where at the boundary these two connection fields are touching each other somehow. So that's the reason why in the counterterms with a K, somehow they should appear a double parametric integral. Once again, we didn't invent anything, we just use it in a different context. So because in Einstein gravity, whenever you want to evaluate the Euclidean action, you end up evaluating the volume, because renormalized action is equal to renormalized volume on shell, which is a computation that you would do in standard black hole to reproduce standard black hole thermodynamics. And in standard black hole thermodynamics, you will face the problem that you have a divergent term, because you are integrating in the Euclidean continuation of the on-shell action. You have to integrate between the horizon and infinity. So you have a divergent term in the evaluation of the on-shell action. And you also have the problem, which is the fact that you don't, as internal energy, you don't get the mass of the black hole, what you call Hamiltonian mass of the black hole. Of course, the entropy, you are able to get it because it's a local quantity defined at the horizon, so this is not problematic. But the problematic thing are the quantities defined at infinity. Just the bulk action of Einstein gravity is unable to reproduce the standard thermodynamic behavior. So you don't get the right internal energy, and you get divergent terms at infinity. So this skew, this is properly corrected by the addition of this Euclidean version of the counterterms with a K. They are able to reproduce the missing part of the internal energy to reproduce the existence of a vacuum energy, which is a property of background independent methods to compute the Euclidean action, the renormalized Euclidean action. And it's also useful to get rid of the divergent terms that appear at infinity. So this is a proper way to recover black hole thermodynamics. End of the story. This part is very successful. I mean, it's a simple geometric way of reproducing standard black hole thermodynamics. I would like to, okay, until now is sort of curious. It's a curiosity. So you found some, we were able to find some boundary terms which reproduce the standard black hole thermodynamics to a certain extent. So, and so what? What is the connection with anything else that people were doing in the context of AdS-CFT? So in order to try to understand these sort of things, you have to address this question from different perspectives. And one of them is trying to make connection with, for instance, with the existence, the presence of the Weyl tensor at the boundary and in the bulk. So think of one of the simplest ways to define energy in gravity. And one of the simplest ways of defining energy in gravity is using the wall charges. Usually wall charges do not give you the right energy of the system. But let's use it in the simple way. Let's define a conserved quantity, which uses the bulk Lagrangian, and you are taking essentially derivatives of the bulk Lagrangian with respect to the Riemann tensor. And you are able to convert, for instance, in four-dimensional case, you are able to convert these counterterms with a k in a bulk term, which is the Gauss-Bonnet. And the Gauss-Bonnet, this is the work that we did with Rodrigo and other people. And so you are able to trade off the Chen form by the Gauss-Bonnet term living in the bulk. And so these topological terms enter in the definition of a renormalized Lagrangian, renormalized action. And so you can use the wall formula to derive a charge, conserved quantity, which depend on this combination between the Riemann tensor and the metric, essentially. But if you remember, what is the most general definition, the definition of the Weyl tensor? The Weyl tensor is the Riemann tensor plus the Schouten tensor contracted with the metric, with the skew symmetric product with the metric. And the Schouten tensor is essentially a combination of the Ricci tensor and the Ricci scalar. So for an Einstein space, whenever you have an Einstein space, you are able to convert this Weyl generic definition of the Weyl tensor into the same object that was appearing here. So this tells you that for Einstein spaces, the charges are proportional to the Weyl tensor. And then you are able to make connection between your general definition of conserved quantities with the conformal mass of Einstein-AdS gravity. This is very interesting because it's a simple way to derive through the definition of wall charges and the presence of the addition of topological terms to convert it into the definition of H-de-Carmagnon and thus mass for the asymptotically AdS black holes. So the message of the previous slide is essentially that for the first time you see the Weyl tensor appearing at the boundary. But you also see the Weyl tensor appearing in the bulk. In the simplest case, in the four-dimensional case, is the renormalized AdS action. It's essentially can be cast in the form of McDowell-Mansuri. It's essentially quadratic in this object. This object is some people refer to as AdS curvature. But now you know that for Einstein's space-time, you would be able to express it in terms of the Einstein on the Weyl tensor for Einstein space-time. So that's the reason why I would like to call it pseudo-conformal structure, because it's just hinting at some conformal structure, but this is still a second derivative. It's just Einstein gravity written down in a different way. So there is nothing conformal this far. But it's very interesting because it gives you new properties of the on-shell action. And in particular, it's interesting because the renormalized Einstein-Hilbert action is identically zero for global AdS. and the charges are identically zero for global ADS. So the minimum requirement that you may have for a gravity theory is the fact to be consistent, thermodynamically consistent for the vacuum state. Because is the thermodynamic relation are trivially satisfied, are identically satisfied for global ADS. So the Euclidean action is zero, the nether wall charges are zero for global ADS, and because the nether wall charge is the entropy at the horizon, so everything is consistent, at least for the vacuum state. And this is also true in higher dimensions, higher even dimensions, where you can add the corresponding topological term, the Euler term, and you are able to factorize this in this is just a fancy way of writing down the previous formula. You have a linear term in the Riemann tensor that so it's just the Ricci scalar. So you have just the product of deltas that are essentially the cosmological constant term. And you have at the end, you have this topological term. And it's nice to realize that this is a polynomial. It's a polynomial on the Riemann tensor and this antisymmetric product of this cube, antisymmetric product of the metric tensor, in such a way that you can always factorize this polynomial twice. At least you can factorize it by the Weyl tensor for Einstein spaces twice by a given polynomial of the Weyl tensor. So whatever I said about the four-dimensional case, you can also mimic for the higher even dimensional case as well. So is it true that it had a double zero in global ADS? So the Euclidean action have a double zero for global ADS, and you are able to write it down conveniently as this polynomial of the Weyl tensor. What is interesting? So let's say a couple of words about how to recover the standard holographic renormalization counterterms. It's very strange because here, for instance, you don't see the standard Gibbons-Hawking term. A standard Gibbons-Hawking term is linear in the extrinsic curvature, so it should be obtained from something that contains the extrinsic curvature multiplied by just deltas. That would be, you would end up with a trace of the extrinsic curvature. So in the standard counterterms with a K, there is no such a thing as a Gibbons-Hawking term. If you want to compare with the standard procedure, you have to introduce it, properly introduce it. And you have to introduce you have to add the Gibbons-Hawking term, and you have to subtract the Gibbons-Hawking term from the same formula. And how to compare properly with the standard procedure, you have to expand the fields in the Pfefferman-Graham expansion for any asymptotically ADS space. And if you do so, the extrinsic curvature is expressed in terms of intrinsic quantities. You have a contribution that does not contain derivatives, and the next to lead order term is something that contains is linear in the boundary curvature, is the Schouten tensor of the boundary. And okay, this is a lengthy computation. In this case, is much simpler because it's just the four-dimensional case. But if you do so, you collect terms essentially that doesn't contain the curvature, is linear in the curvature, and so on and so on. And in this way, you're able to reproduce the standard counterterms that they were appearing in the literature. It's a very simple case. What about higher dimensional case? if you try to do it, what would happen? You carry out the same procedure. Here, there is no Gibbons-Hawking term. You introduce the Gibbons-Hawking term. You subtract the Gibbons-Hawking term. Now you expand the extrinsic curvature and start collecting terms ordered by order in a very systematic way. And what you get is this. What you get is actually like cosmological constant term, exactly the one that holographic renormalization prescribed. This term is also okay. And you have certain combination of quadratic terms in the curvature, but the problem that appears is the fact that here you have contraction of the Riemann tensor that did not appear in the standard holographic renormalization procedure. Okay, you are tempted to trade it off by the Weil tensor square terms. If you do such a thing, you almost get the answer, because these three contributions, at least to show how the procedure goes, the three contributions, no curvature, linear in the curvature, quadratic in the curvature, are exactly the same terms as the ones prescribed by holographic renormalization, but you have this difference. In principle, you have a difference respect to holographic renormalization procedure. So, answering the question, are the counterterms with a K the same as the counterterms given by holographic renormalization? The honest answer is almost, or no. To be honest, they differ by this sort of terms in the next to lead order in the quadratic contributions. It appears, for instance, Weil square term at the boundary, and so on, so on. I mean, this as you go in higher derivative expansion, there would be eventually more. The disagreement will be even more serious than this just quadratic terms in the Weil tensor. So what we got somehow disappointed by this observation, and we thought it was truly a problem of the method, because whenever you arrive to this stage, you can just drop the second term, but the point is that the last term is 0 for most of the asymptotically AdS space. If you want to evaluate Euclidean action, the Euclidean action for asymptotically AdS black holes, most of these solutions will have 0 contribution coming from the Weil tensor of the boundary. But the problem appears whenever you want to deal with, for instance, gravitational instantanes, which have a less trivial behavior for the boundary Weil tensor. So one alternative will be being a shameless person and just simply adding something, but it will be against of all our principles, and you will construct such a thing as Frank Einstein-AdS gravity. If you have to add by hand, it would be very ugly. It would be as ugly as Frankenstein. So all the point of this seminar is trying to find an alternative way of correcting these problems of counterterms in a more fundamental way, not in this way of just adding by hand something to cancel the presence of the Weil square at the boundary.
Rod?
Yes.
Yeah, you have 5 minutes.
Wow. Okay, I will run. So where the answer could come from? The answer could come from a very simple observation, which is the fact that in the 4-dimensional case, this form that I showed to you McDowell-Mansouri is actually could be consistently embedded in a conformal gravity theory. So conformal gravity is finite. So if you have a sector of your theory, of your conformal gravity theory, which contains an Einstein sector, in particular Einstein-AdS solutions, the renormalization should be inherited by this sector of. So if you have a well-defined mechanism to switch off certain modes, you could go between conformal and Einstein gravity, such that the renormalization should be inherited by the Einstein sector. And this is the idea. And this will be very fastly reviewed. There is a paper by Maldacena in 2011 who was claiming that there is a consistent way of switch off certain modes in certain higher derivative modes and go between conformal gravity and Einstein sector of conformal gravity. And this is made explicit in the Fefferman-Graham expansion for asymptotically AdS spacetime in conformal gravity. In conformal gravity, there are higher derivative modes that if you take Neumann boundary conditions, you will be able to end up in the Einstein sector of the theory. So in particular, conformal gravity contains Einstein solutions. It's a sector of the theory. So if you have some precise boundary conditions which realize what Maldacena was claiming, in particular, for instance, the definition of an Einstein space can be translated into the traceless part of the Ricci tensor. If you ask the traceless part of the Ricci tensor to be 0, that means you are considering Einstein spacetimes. And in this way, you are able to realize holographically this being able to go between solution of conformal gravity and the Einstein sector of conformal gravity. And you have to fix certain holographic data in a precise way, and you are able to reproduce the Einstein sector. What we did recently, we were able to find a particular conformal gravity theory, which correspond to a precise combination of conformal invariants in 6 dimensions, which contains an Einstein sector. This particular conformal gravity theory is called Lupin and Pope. It's a precise combination between the 3 conformal invariants, and they're essentially certain contraction of the Weyl tensor, certain contraction of cubic terms of the Weyl tensor, the Compton tensor, and in order for the gravity theory to be conformally invariant, you have to consider additional boundary terms. And to make the long story short, I will mention the fact that there is a consistent way of demanding showing that Einstein's solutions are solutions of Lupin and Pope gravity theory. And in doing so, one of the guiding principles is the fact that because the theory contains powers of the Riemann tensor, these powers of the Riemann tensor could only contribute to the existence of a topological term, because you want to reduce to Einstein gravity theory. And the only way you can do such a thing is that at the end of the day, taking Einstein condition in the Lupin and Pope gravity theory, you are able to reduce it to Einstein-Hilbert plus Euler 6 is what we have in this way of adding topological terms to renormalize the action. But whenever this procedure is carried out, there is an additional term. It appears an additional terms that depends essentially on the Weyl tensor for Einstein spaces. And as a consequence, the difference with respect to the counterterms with the K procedure, there is an additional terms that if you expand in powers in Pfefferman-Graham in powers of the radial coordinate, of the holographic coordinate, and you reduce it to the Einstein form, and you power count, etc., the difference is exactly what you needed in order to match the holographic renormalization prescription, even with the factors and so on. So it cannot be just a coincidence that if you start from a conformal gravity theory and you reduce it to the Einstein sector, the holographic renormalization prescription is trivially realized. So at the end of the day, just to conclude, is that this way of renormalizing is just required to embed your Einstein gravity in a corresponding conformal gravity in the corresponding dimension. Is there little evidence because we just have the evidence of four-dimensional case that is somehow trivial, but the six-dimensional case is already less trivial than before. And you saw that the mismatch between holographic renormalization prescription and the counterterms with a K is exactly given by this way of conformally renormalize. So it is open the question how to proceed in higher even dimensional case. This is an open problem because you don't even have a full basis of conformal invariance in higher dimensions. This is a subject of current investigation with some collaborators. And of course, we are also interested on the consequences of this way of renormalization on codimension 2 objects. That means area renormalization or the corresponding functionals that appears in codimension 2. That is, of course, our interest in defining holographic entanglement entropy and other quantities that you can use it for. Thank you.
Okay. Thanks, Rodrigo, for the nice talk. Is there any question from the audience? I have a question, but it's quite silly. There is some attempts to construct CFTs with boundaries by Takayanagi in 2011, I think, or around those years. The point was to allow the metric to fluctuate. So you instead of having Dirichlet boundary conditions, you use Neumann, which gives you some constraints on the extrinsic curvature, some equation, and you can still use standard holographic renormalization procedure. Could you use counterterms in this with this new?
I guess so, because it's exactly what I'm pointed out. Because what you saw from the general asymptotic form of asymptotic AdS spacetime is the fact that the extrinsic curvature can fluctuate. I mean, because it's just enough to demand that the extrinsic curvature is proportional to the boundary metric. It's not fixed. You are not saying anything. I mean, in the standard context, you demand fixing G naught at the boundary, but eventually you could ask for other sort of boundary conditions.
Okay. If you so you're matching conformal gravity or some sector to construct renormalized Einstein-AdS, but what about?
It's just inherits. Yeah. It's inherited. I mean, if you it's somehow a different. It's a change of paradigm. It's just instead of renormalizing and carrying out the whole procedure, you just say conformal gravity should be finite in a way. You don't need counterterms for conformal gravity. So in a way, if you particularize in a sector in conformal gravity, everything should be already finite.
Okay. And is there any like finite gravity theory in odd dimensions? Because there is no conformal gravity, not right?
This of course is an open question. Because the only conformal gravity theories that we know, they are living in even dimensional case. Whatever you can construct in all dimensional cases should be something associated to the conformal group. So Simon's associated to the conformal group or something like that.
Yeah, I see. Okay, so is there any other question by the guys? Well, if not, we can say thanks, Rodrigo, again for the talk. So
Thank you.
you can clap or I don't know. I will stop the recording.